subject, talk about stretch activated channels. Stretch activated channels. Sometimes they're also called stress, S-T-R-E-S-S activated channels. So stretch or stretch activated channels. And one place in which these channels are located is in the inner ear. This organ designed for detecting sound. There's an eardrum, a couple of bones that amplify that sound waves, in fact, amplify the signal. Take that signal to a fluid-filled labyrinth of vesicles called the cochlea. And it's at that point that there are sensory cells which have stress-activated channels. And these are called hair cells. If you stretch out the coil of cochlea, you find really a sort of two-chamber structure with a layer of cells in the middle, and on those are hair cells. The hair cells, one of them is shown here, one here, one here. They're at their apical end have these extensions. They're called stereocilia. They're not true cilia. They're filled with actin, so they're more like they're actin-filled, and they project up into this fluid-filled space here. So this is the hair cells. The hair cells contain stretch-activated channels. Here's another image of the top of one of these hair cells in a bullfrog. Okay? So stereocilia. And in response to movement, these cells will move these stereocilia and open stretch-activated channels, allow ions to move in through those channels and depolarize the membrane. So I'll show you a movie which describes this. This is another movie from your book, so you can have a look at it.
Within our ears are called hair cells. Each has a tuft of spiky extension called stereocilia on its upper surface, and each sends signals to auditory nerves through its basal sheath. The hair cells are embedded in a sheet of supporting cells and are sandwiched between two sheets of extracellular matrix, the tectorial membrane and the basilar membrane. Sound vibrations cause the basilar membrane to vibrate, and this motion pushes the stereocilia into the tectorial membrane. The stereocilia bend, triggering an electrical response from the hair cell. The activated hair cell, in turn, activates the auditory nerve. The hair cell is activated by stress-activated ion channels. These channels are closed when the stereocilia are not tilted. However, when they tilt, a linking filament from one stereocilium to a channel on a neighboring stereocilium pulls at the channel, opening it. Positively charged ions flow into the cell, depolarizing the membrane.
So once again, the mechanical deformation of the membrane and associated proteins in the membrane, these ion channels, which open in response to that deformation. That's the hair cell of the inner ear. So actually similar hair cells season still in Ohio. It's still cold outside, even though it's second day spring, so we have this lot of hot chocolate.
We couldn't hear it.
What was the answer? Queen and Freddie.
Oh.
This is Queen and Freddie Mercury. Maybe I'll play some of it later. People need education about music. The reason I show this is because of the sound amplification systems that are used by rock and roll bands. And this is a representation of the normal cochlea with normal hair cells. Here is after being in a rock and roll band for some years. So these hair cells become damaged by loud noise, jet airplanes, jackhammers, those sorts of things, perhaps loud music. So these rock and roll musicians are cranking up the amplifiers all the time. And so you can actually see scar tissue in the cochlea as a result of damage. So the hair cells are not going to open properly, stress-activated channels won't open properly. So watch out for loud noise. I mentioned the motion detectors and gravity detectors. They're in similar fluid-filled cavities in the inner ear as well. And they will respond by opening those stretch-activated channels, depolarizing the cell, and then releasing neurotransmitters which will act on the other cells to take that information to the rest of the body. Okay. So, I'd like to have you test your knowledge and look at glucose transport in the intestine. Glucose is transported from low concentration in the gut into the intestinal cells and out the other side where it's taken up into the blood. So could you develop a model which permit glucose to be transported through intestinal cells? So in your groups, come up with a model. You have a variety of ways of thinking about transport and how things might move across cell membranes. There's lots of possibilities that could be valid for transporting glucose across an epithelial, into and across an epithelial cell of the intestine. So see if you can come up with some ideas of how it might work. You are not allowed to look in your textbook. You're not allowed to look in your textbook.
What were you about?
Okay, try it.
Right. Right on.
Draw a picture of the cell. See what else you might need.